Welcome to Future Epoch, where we learn more about our world. Every year, humanity releases roughly 37 billion tons of carbon dioxide into the atmosphere. Scientists, engineers, and governments have spent decades debating how to stop adding more. But a quieter, more technically ambitious question has been growing alongside that debate. What if we could not just stop adding CO2, but actually take it back? Carbon capture and storage, the idea that we can pull carbon dioxide out of emission streams, or even directly from open air, compress it, and bury it underground, is either one of the most important technologies of the 21st century, or one of the most expensive distractions in the history of climate policy. Possibly both. The basic principle of carbon capture is straightforward. Industrial processes, burning fossil fuels, making cement, refining steel, release CO2 as a byproduct. Capture technology intercepts that CO2 before it reaches the atmosphere, compresses it into a dense fluid, and injects it into deep geological formations where it is expected to remain trapped for thousands of years. A second, more ambitious variant skips the industrial source entirely. Direct air capture pulls CO2 straight from the open atmosphere, where it exists at a concentration of around 420 parts per million. This makes direct air capture theoretically capable of addressing historical emissions, not just new ones, but the dilute concentration of CO2 in air makes the process vastly more energy-intensive and expensive than capturing it at the point of emission. Both approaches have been tested. Neither has been deployed anywhere near the scale that climate models suggest is needed. The story of industrial carbon capture begins not with a climate emergency, but with an economic calculation. In 1996, the Norwegian energy company Statoil, now known as Equinor, began injecting CO2 into a saline aquifer beneath the North Sea at its Sleipner gas field. The motivation was financial as much as environmental. Norway had introduced a carbon tax on offshore operations, and injecting CO2 underground was cheaper than paying the levy. Sleipner became the world's first commercial-scale carbon storage project, and it has since stored more than 20 million tons of CO2. Progress after Sleipner was slow. Through the 2000s, governments and energy companies announced demonstration projects, but most struggled to move from planning to operation. The cost of capturing CO2 at a coal-fired power plant, the most widely discussed application at the time, was estimated at between $50 and $100 per ton, adding substantially to electricity generation costs. A handful of projects did advance. Canada's Boundary Dam facility in Saskatchewan began capturing CO2 from a coal plant in 2014, becoming the first post-combustion capture system attached to a commercial power station. Quest, a Shell-operated project in Alberta, began injecting CO2 from oil sands operations in 2015. The Illinois Industrial Carbon Capture and Storage Project, supported in part by the U.S. Department of Energy, demonstrated that ethanol production could be paired with deep geological storage. But for every project that reached operation, several others stalled, ran over budget, or were cancelled outright. The Kemper County Energy Facility in Mississippi, intended as a flagship American CCS demonstration, became a cautionary tale. Originally budgeted at around $2 billion, it eventually cost close to $7.5 billion and was converted to run on natural gas before its carbon capture system ever operated at design capacity. The fundamental tension in carbon capture is one of scale. Current global CCS capacity sits at roughly 50 million tons of CO2 per year across all operating projects. The International Energy Agency has estimated that reaching net zero emissions by 2050 would require capturing and storing more than 7 billion tons annually by mid-century. That is an increase of more than 100-fold from where the technology stands today. The obstacles are not primarily scientific. Geologically, the world has ample storage capacity. Estimates suggest that depleted oil and gas reservoirs and deep saline aquifers could accommodate hundreds of years' worth of global emissions. The barriers are economic, political, and logistical. Capture equipment is expensive to build and maintain. Pipelines to move CO2 from emission sources to storage sites require substantial infrastructure investment. And monitoring geological storage over decades and centuries requires regulatory frameworks that barely exist in most countries. Direct air capture has attracted significant investment and attention in recent years as projected costs have fallen, slowly, from figures above $1,000 per ton toward estimates below $300 per ton at scale. In Iceland, the company Climeworks operates a facility called Mammoth, the largest direct air capture plant in the world as of its opening in 2024, with a designed annual capacity of 36,000 tons of CO2. Impressive as a proof of concept, this represents a fraction of 1% of annual global emissions. Critics argue that the billions of dollars being directed toward carbon capture would produce better climate outcomes if spent on renewable energy deployment or efficiency improvements. Others, including the Intergovernmental Panel on Climate Change in its assessment reports, argue that carbon removal is not optional, that the emissions trajectory of the past several decades has made some level of active removal necessary to meet temperature targets, and that multiple approaches must be pursued simultaneously. This is not a disagreement about the science of capture, it is a disagreement about priorities, risk, and how to allocate finite resources. The consequences of scaling carbon capture, or failing to, cut in several directions. For heavy industry, CCS represents one of the few technically credible pathways to deep decarbonization in sectors where electrification is difficult or impossible. Cement production releases CO2 as a direct chemical byproduct of the calcination process, not just from the energy used to heat kilns. Steel production at industrial scale still largely depends on coking coal as a chemical reducing agent, not merely as a fuel. For these industries, carbon capture is not a delay tactic. It may be the only viable low-carbon option available with current materials and processes. For fossil fuel energy, the picture is more contested. CCS has been proposed as a way to allow continued use of coal and gas while meeting climate targets, and this framing has made it politically divisive. Environmental organizations have argued that attaching capture systems to fossil fuel plants prolongs infrastructure that should be retired. Proponents respond that gas-fired generation with carbon capture produces far lower life cycle emissions than gas without it, and that the transition to a fully renewable grid will take decades, during which some dispatchable generation will remain necessary. There is also the question of what happens underground over the long term. Most experts consider geological storage of CO2 to be highly stable, and monitoring at sites like Sleipner has not revealed unexpected migration of stored gas. But monitoring over geological timescales introduces uncertainties that current science cannot fully resolve. An unexpected release from a poorly chosen site or from seismic activity would undermine both the safety case and the political credibility of the technology. The most important thing to understand about carbon capture is that it is not a silver bullet, and it is not a distraction. It is a tool, one with genuine potential and genuine limitations, currently deployed at a scale that is orders of magnitude smaller than what would be required to matter at a global level. The gap between what exists and what is needed is not primarily a gap in scientific understanding. The technology works. The gap is in finance, policy, infrastructure, and political will. Several countries have introduced carbon pricing mechanisms that make geological storage economically viable under certain conditions. The United States, through the Inflation Reduction Act, significantly expanded tax credits for carbon capture and storage, creating new financial incentives that have prompted a wave of project announcements in the early 2020s. Whether those announcements translate into operating projects at meaningful scale is the central open question. History suggests reasons for caution. We have spent more than a century building a civilization that runs on carbon. The question that carbon capture poses is whether it is possible to partially unbuild the atmospheric consequences of that civilization without dismantling the civilization itself. The honest answer is that we do not yet know. The technology exists. The geology is largely willing. But the economics have never fully worked at scale. the infrastructure has never been built, and the political consensus required to sustain multi-decade investment has proven elusive in nearly every country that has attempted it. What seems clear is that the window for finding out is narrowing. The decisions made in the next 10 to 15 years about which projects get built, how they are financed, and where they are sited will largely determine whether carbon capture becomes a meaningful part of the climate response or remains a promising idea that never quite arrived. The atmosphere does not wait for funding rounds to close or political cycles to turn. The carbon that enters it today will still be there in 100 years, whether or not we ever find a way to bring it back. Thank you for watching. If you've enjoyed this content and want to see more, please consider liking the video and subscribing to the channel.